Welcome to our next lecture in the series on condensed matter theory. In this video I want to talk about ligand field theory. And ligand field theory is one of the older methods to describe the properties of solids. It was developed recently, quickly after the introduction of the Schrödinger equation, when people realized that approximating a solid by a potential is not sufficient. They looked at different hybridization theories where the orbitals locally interact with orbitals non-locally. And this then condensed into a single theory called ligand field theory. The theory that we use is sometimes also called multiplet ligand field theory because we truly take all the local interactions into account and consider all the many-body multiplets. The language that I will use in order to introduce the ligand field theory is slightly different from what you might find in the standard chemical textbooks. I want to be able to continue from ligand field theory to Anderson impurities to dynamical mean field theory, and I want to relate the parameters that we find to those that you can obtain within a density functional theory calculation. And as such, we'll just use the language that is fitted to do so. What we have discussed before is that we can write the wave function of the full solid as a sum over the different configurations and the states within that configuration, and then a prefactor where we look at the wave function of a single side, side I, where we have the atomic states of the configuration with angular momentum L and N electrons, and state I in that configuration, and then multiplied by a Bath wave function. These are all many-body wave functions. And the Bath wave function is the wave function of the solid without the local state, with configuration Ln and state J of that configuration missing. Now, if you think of representing these states, then the local atomic wave function is given on a finite Hilbert space. Whereas the Bath wave function is given on an infinite Hilbert space. And we're looking at the wave function of side I, or we look at the exact representation on side I, and of course this can be any side, but when I take one side or the other, my Bath wave function will change. If you have a solid made out of a single atom, then of course there should be a relation between the Bath wave functions, because your entire system should have translation invariance under a lattice transformation. If you have different atoms within a unit cell, then you really have different Bath sides that are unrelated. And on side I have the configuration of L and N electrons in the L shell, and the wave function is given for state J within that configuration. And this is valid for all sides. Now, calculating a correlated wave function on an infinite Hilbert space scales exponentially, so it's really a large infinite that we have here. We have an infinite one-particle states, and therefore you have an infinite over infinite number of many particle states. So this is truly an object that well, you cannot even represent or think about how to represent this. So we do not want to know our baud wave function. Because it is just not an object that is handleable. Now we know that in order to represent physics, you do not need to know your wave functions. Just think about density functional theory. When we do experiments, you measure response functions. So what we are after is ways to express our response functions of the solid without explicit knowledge on the baud wave function. But we are allowed to have explicit knowledge on the local wave functions, because that is given on a finite Hilbert space. So we're looking for the response functions. My pen is stopped working, so we can think of the response functions where we look at the propagation of a single electron, and in order to not having to look at the causal response functions, which have imaginary parts that are both positive and negative, I will have a look at the Green's functions. And of course, with the use of the Green's functions, we can always reconstruct the response functions. And we can look at the 1.1 particle Green's function, where you start in the vacuum and create one particle. And this should be, of course, now your many-body wave function. And look at its propagation, omega minus h plus I0 plus a tau prime tau. And we can equally well look at the 4-point Green's function, where we create a particle, have a propagator, create another particle, have a propagator, and then we annihilate a particle, let the system propagate again, and we annihilate a particle and see if we get back to the ground state. And then of course we can have the 3-particle or the 6-point Green's function, etc., etc. And note that instead of creation and creation, we can also look at creation, annihilation in this case. Creation, annihilation, to look at the different possible Green's functions. And here as well, instead of first creating and then annihilating, we can first annihilate and then create. So there are several Green's functions that we can look at, and in principle, if we know those Green's functions, we can calculate the response functions of the system. And with that, we know all possible experiments, or we can describe and predict all possible experiments that one can do on a system. So the question that we need to ask is, can we make an approximation to the baud wave function such that the Green's functions do not change? And that of course means as much as possible. We'll find ways to make extensions such that when you include more and more, you will not change all your Green's functions, but we can start, of course, with some approximations. And in order to introduce how one should be able to do this, Let's start on a mean field level and then see how we can expand this until we can reproduce the exact local Green's functions of our lattice. So we will work around a mean field approximation. And of course it's important not to have perturbative expansions around mean field, but look at methods that converge and are non-perturbative. So on a mean field level, we can think of our Green's functions by looking at the vacuum Green's functions, where we create a particle tau out of the vacuum and we now have only a single electron. Then we have the propagator given by the mean field Hamiltonian, and we annihilate a particle in a different orbital and see if we get back to the vacuum. Now, if we look at our local Green's functions, where we want to consider an L shell or a shell with a certain angular momenta, a single shell, then our Green's function can be represented by a matrix. Is a matrix, and it has dimensions of 2L plus 1 for the orbital degeneracy times 2 for the spin degeneracy. So tau can be one of the m quantum numbers or the Lz quantum numbers for your angular momentum, and can be spin up or spin down, giving you a 2L plus 1 times 2 degeneracy. And with that we then have a local Green's function as a matrix. Now I want to be able to talk about the local side and the bath. So I want to know what the influence is from the local Hamiltonian and the bath on my Green's function. So for this we can always write our Hamiltonian as a sum over the local Hamiltonian on a mean field level, and that is the Hamiltonian acting on the L shell on side I plus the rest. So that is the bath Hamiltonian plus H bath side Li. Now, in order to capture what the rest is doing in terms of Green's functions, I will introduce a hybridization function. Which is again a 2 times 2L plus 1 matrix. And we will write our Green's function within mean field, or our matrix, as 1 over omega minus H mean field acting on side I and the L shell minus the hybridization function plus I0 plus, to make sure that our poles are below the real axis. Now we can of course solve this for our hybridization function, and our hybridization function is omega minus the mean field Hamiltonian acting on side I minus the mean field Green's function inverted, and this is a matrix inversion. Now our hybridization function tells you what the influence of the bath is on your local states. So it tells you how locally your states interact with each other due to the effective hopping in and out of the bath. We can make this also an explicit hopping. So we will define a hopping strength, and that is T, which is frequency dependent. We will make this again a matrix that is Hermitian, and we now define that t square, again matrix multiplication, these are all 2 times 2l plus 1 matrices, is given by minus 1 over pi, the imaginary part of your hybridization function. So the hybridization function is some sort of self-energy, how the rest of the system changes your local states. Therefore, it is related to a Green's function, a response function, or parts of the response function, how your local state responds to the interaction that you have with the neighbors. Therefore, if we take the imaginary part, that becomes some form of densities of states. The imaginary part must be strictly negative, such that if I take the minus part, it is strictly positive. And we can now take the square root of that positive number or positive definite matrix. And that then gives you the hopping amplitude, T. Now, why do we define this as a hopping amplitude? And that becomes clear if we look at our original mean field approximated Green's function. Then this is 1 over omega minus our mean field Hamiltonian acting on the L shell at side I, minus, and then instead of delta of omega we can now use that this is equivalent to hopping to a bath side at energy omega prime with hopping amplitude T. And of course our small imaginary part. In order to understand how we go from delta, the hybridization function, to an explicit hopping, we can have a look at a finite Hilbert space. We have discretized our energies and look at the matrix inverse. If I look at a matrix where I have omega minus H mean field acting on the L shell of side I, and then an hopping with frequency 1 at frequency 2 at frequency 3, and then on the diagonal omega minus omega 1, omega minus omega 2, omega minus omega 3. We invert it and we look at the element 1, 1, where of course we should realize that each of those blocks are 2 times 2l plus 1 by 2 times 2l plus 1 matrices. Then this inverse is exactly giving you the inverse that we have here. We've saw this for single states, but you can expand this to many states, and then it's just the inverse of this full matrix restricted to the first block is given by the function that we have here. For a finite Hilbert space, that becomes a sum. For an infinite Hilbert space, that becomes an integral. So that's where we can now replace our hybridization function by an explicit form of a time-binding Hamiltonian again. So what we find is that our mean field Hamiltonian that reproduces the same Green's function as the original mean field Hamiltonian is given by the local mean field Hamiltonian plus a sum over all orbitals that we have within our local Hilbert space. So tau goes from 0, 1 to 2 times 2l plus 1. And then an integral, because we have an infinite number of bath sides, where we have the energy of our particles that occupy a bath side with energy omega, plus, and then we have the interaction between the local and the local states and the bath states by hopping t prime of omega a dagger omega t a t prime plus its harmonic conjugate integrated over all frequencies. So you can change your tight binding Hamiltonian without changing your Green's functions. And that is of course very nice, because this allows you to make effective models without changing any physical observables. And of course we only focused here on the one particle Green's function. If you want to be fully self-consistent or fully get the full solution, you also should focus on the two particle or 2, 3, 4 point Green's functions. But let's start by just looking at the one particle Green's function. And of course we should go beyond mean field to get the full answer. Now with this in mind, we can have a look at ligand field theory. And in ligand field theory, we say that our full Hamiltonian will become the mean field Hamiltonian. So we do make a mean field approximation, but then we subtract the local mean field Hamiltonian and we add the full local Hamiltonian. So we treat all sides on mean field except for the local side, where we include all interactions. Now on the mean field level you can get potentials, and you can generate your potentials such that your density is well reproduced. And in this sense you can say that ligand field theory wants to look at your response functions but doesn't really look at the energy dependent Green's functions, but only focuses on a self-consistency between the local side and the non-local sides of the integrated over energy Green's function or your charge density. So this is a static mean field theory where you locally include all interactions and non-locally have a potential such that your densities of the local impurity with all interactions is equal to the density on the non-local sides. Now we'll make a few more approximations to get to ligand field theory, because this is what you get in principle in Anderson impurity model, where we have an infinite number of uncorrelated side acting with correlated side, and that is still an infinite dimensional Hilbert space. Now what we want to do is reduce the dimension of the infinite bath. In order to do this, it becomes important to realize that you are allowed to make linear combinations of bath sites, but when you linear combine bath sites that are above the chemical potential and bath sites that are below the chemical potential, you start to mix occupied with unoccupied bath sites. And in the end you do want to have an integer number of electrons on a finite Hilbert space. So you do not really want to have mixed occupied and unoccupied states. So we have to realize that we set our chemical potential to 0. You can always of course change this by replacing my omega by an omega minus mu, and then you can choose the chemical potential at the end of your formulas. So what we're going to do is we have an integral where we integrate over the interaction with all bath sides, and this has to be strictly replaced by an integral up to 0 plus an integral from 0 to infinite over your bath sides. So you strictly have to separate the occupied and the unoccupied states. Now if you look at your hybridization function that encodes the influence of the bath on your local impurity, then this is a function as a function of frequency, and we now want to discretize this function, and for that you can define intervals and say, well, I'm going to look at the hybridization in different intervals, and maybe close to the chemical potential you want to make smaller intervals, and then far away you can maybe make very large intervals. And these intervals have a width of delta omega e, delta omega I, and then of course at the center of each interval we're going to define the energy that we have. Now I'm going to take my omega i's centered within the interval, and I'm going to allow the interval width to be flexible. So we know that omega I plus a half delta omega I has to be equal to omega I plus 1 minus a half delta omega I plus 1. And we had our chemical potential where we want to make a strict separation. So we should have that our chemical potential sits at a boundary between the different bath sites. So there must be an I such that omega I plus half delta omega I is equal to 0. And with that we have defined a sensible way to discretize our hybridization function. Now, when you want to calculate what the hybridization strength at each energy omega I should be, one can realize that you would like to keep the moments of your hybridization function, or your local moments of your hybridization function, as conserved as possible. And with that you can define integral equations for your hybridization. So the hybridization at a given frequency can be related to just the integral over your discrete interval of the full frequency dependent hybridization function. If your hybridization is constant, then this would just be the energy width times that value. If it varies, then it's going to be the average of that interaction. And now we can also define the energy at which you have your hybridization. Well, in first order you could of course assume that this is just the center of gravity of that energy, but we can be a bit more accurate and we can look at the first moment and make sure that our first moment is conserved. Omega times the trace of T dagger omega, T omega, the omega divided by, and then the integral without the omega. Note that with this definition we have all orbitals hybridizing with the state at the same energy. In principle you are allowed to make this omega dependent. When you do that you have to be a bit careful that the definition that you use does not change under unitary basis transformations. So physics is independent of the basis that you choose. So any physical valid definition must be invariant under local basis transformations. Now, of course, the trace is invariant under local basis transformations, so the definitions that I made here fulfill that condition. T dagger T is because T is Hermitian, a definite positive, and therefore you can integrate. If you would just average the hopping, then you might have cases where you have strong hopping with a positive phase at one energy and a strong hopping with a negative phase at another energy, and that would average to 0. So you wouldn't be able to just average the hopping matrix elements, but you can average the square of a hopping matrix elements. And you can always take square roots of matrices again, under the condition that your square root is Hamiltonian. The question that you in principle should answer is how to optimize the discretization of a continuous function. There's of course a lot of things done in that direction in signal theory. And what I show you here is an option where you are free to choose your discretization points. There are other options that you can think of and choose. If your matrix is diagonal for all frequencies, or you can make it diagonal for all frequencies on the same basis, then you would in principle define here a different energy for each of the orbitals. That would be a simple improvement over what we write down here. But that's more details that we don't have to go in at the moment. What we will find after you have discretized your Bath or hybridization function is that our mean field Hamiltonian is given by the mean field Hamiltonian for side I with shell L plus a sum where we sum over all orbitals and then all discrete Bath states that have a discrete energy, and then the on-site energy of the electron being in the bath plus a sum over again all Bath states, and now the orbitals that we have where you can hop with the hopping amplitude that is state dependent, and the interaction between your impurity and the bath. Now what we have here is n discretization points. And we discretized the hybridization function, and our hopping is proportional to the square root of our hybridization functions. So if your hopping is frequency independent, then the hopping that we get in between omega min to omega max, and we take n points in that interval, then your hopping will be square root 1 over n times t times omega max minus omega min. So use hopping scales with 1 over the square root of the number of discretization points. Now, in order to get a little bit more of a feeling what is going on in this formalism where we talk about hybridization functions, we can also derive exactly the same result, but now starting from a tight binding model, and also there get to a local Hamiltonian interacting with a bath with a discrete number of bath states that you can build up starting from the local states. And for that we'll start from a tight binding model. So in our final model we want to have a local set of states which we will treat with all many-body interactions, and then have this local set of states interact with the non-local states approximated on a mean field level. And the question that we need to answer is which non-local states do we have to include. So we start from a local one-particle basis. And let's call those phi tau 0. We now can define our path states, and I put a tilde on top because they are not yet orthonormalized, and we define them by taking our full mean field Hamiltonian and acting on our local one-particle basis. This will generate new states, because, well, if you have a tight binding Hamiltonian and you start from a local orbital, then the hopping will allow you to generate a particle in neighboring states. If your hopping phase is such that it's positive in both directions, then you will hop out to both directions, both with a positive phase, such that your new wave function will become a linear combination of an electron at state I-1 and state I+1 with a positive phase in between there. If your hopping amplitudes have different strength, then that strength will be represented in your Hamiltonian, such that you get that immediately into your new basis state. And we then will orthonormalize this state, psi tilde tau 1, to get our basis states. And this is our first baud state. Now we want to generate in the end an infinite dimensional set of baud states that we can truncate or that we can reduce, and for that we can define our n+1th baud state by acting with the Hamiltonian on baud state number n. And again, in order to go from tilde to the real baud states, we have to orthonormalize that state. If we have n baud states, then we generate a basis for the baud by the states that are spanned by h psi tau 0 up to h to the power n psi tau 0. Now, in order to see how this basis that we generate here, which is known as a Kriloff basis, is related to the Green's functions that we used before to define a hybridization function, we can realize that if we look at our Green's function in the time domain, then the Green's operator is related to the time evolution of your system. And if we now make a Taylor series expansion, then this is the sum n is 0 to infinite 1 over n faculty IHT to the power n, such that our Kriloff basis spans the first n orders of the Taylor series expansion of the Green's function in the time domain. So if we go up to infinite order, we get back to having a full basis for our Green's function. Now we can have a look at a pictorial representation of these different ways to look at your local impurity and how it interacts. If you think of the Kriloff method, then we start with the local impurity, and then we acted with our Hamiltonian on that state, and that generated the first baud state. Then we acted with the Hamiltonian on that first baud state, so this is now the hopping. And when we act with the Hamiltonian on the first baud state, we generate the second baud state. Of course, you also generate states that are the local impurity again, but we orthonormalized. If there would be a direct hopping between the local impurity and the second baud state, then you would have generated that part of that state the first time already, and because we want this state to be orthonormal to the first bath state, there is no possibility to directly hop from the local impurity to the second bath state. And the same holds when we have the third bath state or the fourth bath state, etc., etc. So within the Kriloff method, you will generate, in principle, a one-dimensional tight binding Hamiltonian, where the endpoint of your one-dimensional tight binding Hamiltonian is the correlated state, where you want to look at all your interactions. So we transformed our mini-body solid into a local correlated impurity interacting with a mean field approximated one-dimensional chain. So that is the Kriloff method. And then of course you can truncate your chain at some point if you want to go to a finite Hilbert space. The hybridization function starts from your local impurity, and then we had an interaction given by T, two states at specific energies. So this is now frequency, and this is omega I, discrete energies, and this is T of omega I, and the discrete hopping. So the hybridization function gives you the interaction between your local impurity and a diagonal or a diagonalized bath. There's no interaction between the bath sides anymore. The Kriloff method gives you the local impurity interacting with a one-dimensional tight binding chain. Of course, going between one and the other is just a unitary transformation. You can diagonalize your bath that you get with the Kriloff method, and then you get the hybridization function. The bath as you would have gotten from the hybridization function that is diagonal. So there is a unitary transformation between them. Both methods are equivalent in the limit where you have an infinite number of bath sides. The Kriloff method gives you a certain set of bath states, whereas for the hybridization method you can in principle choose the energies where do you want more accuracy and more focus, and where do you want less accuracy and focus. So this gives you slightly more control over the approximation that you want to make in the end. It turns out neither of the two representation is the most efficient in the end, but that would go too far for the lecture that we discuss at the moment. Now, this is true for a general Anderson impurity model. What we want to focus on in this video is the ligand field theory. And in ligand field theory, we're going to keep one bath side. That's quite a big approximation. We'll lose all information about band formation, but for strongly correlated insulators, it's not so bad. And the previous approximation where we discussed in principle a system where we kept zero bath sides, we neglect all charge fluctuation, we now at least have the possibility to do some charge fluctuations. And of course, we can already think of ways to improve on it, and we can, instead of keeping one bath side, keep two bath sides or three bath sides, and in this way build up more and more realistic models of the system that we have. But let's focus on just keeping one bath side. And the bath side that we're going to keep is one of the occupied states. So a valence bath side. Now for your hybridization function, you have your chemical potential somewhere, so you just say I want to reduce the interaction with all the ones below the chemical potential. In the Kriloff based method, that's of course a bit more tricky to see how this should be a state that is fully occupied. But then let's have a look for the materials where ligand field theory is actually developed, and just have a look at something like nickel oxide, a strongly correlated transition metal oxide. And for that we have locally a nickel atom, and that nickel atom is 6-fold coordinate by oxygen atoms, such that your lattice, if we just focus on a two-dimensional cut, is giving you a checkerboard order between nickel and oxygen atoms. And this then extended to 3 dimensions, where you have alternating nickel and oxygen atoms on a square lattice. So if we just focus on nearest neighbor interaction, then it is always a nickel that hops to an oxygen and vice versa, an oxygen that hops to a nickel. Now if we look at the formal valence, the ionic configuration that we have, the nickel is 2+, and it is the s electrons that you had in the atom but no longer in the solid. So we say that nickel has the configuration 4s0 3d8, and the oxygen is 2-, which becomes a full shell 2p6. Now if you look at the local basis that we have for the d shell, then this is given by the x square minus y square, or the z square orbitals, which belong to the EGs, and then the yz, the xz, the xy, which are the t to g orbitals. If you now say I start with those local orbitals and I act with my Hamiltonian on it to generate my ligand orbitals or my path orbitals, then in the first step the electron at the nickel will hop to an electron on the oxygen, or a hole on the nickel will hop to a hole on the oxygen, and therefore you do indeed find that your first bath state is fully occupied. The second bath state you will be able to hop from the oxygen to the nickel again, and then you get mixtures of occupied and unoccupied orbitals. Actually, we can have a look how this looks like graphically. That immediately shows you what your ligand orbital would look like. Let's put in the phases. Solid is minus, open is positive of your orbitals. And then we have 4 oxygen atoms in this plane. Now this, if this would be the xy plane, this xy orbital cannot hop to the z direction, because their all hoppings are 0 by just the symmetry and the nodes in your wave function. But if we take this xy orbital and hop in this direction, then it cannot hop to a pz, or that's pointing out of the plane to a px orbital, just because the lobes have one positive, one negative sign. But it will hop to an orbital that has this shape. Now at the same amplitude it can hop into the other directions to a single very specific orbital. It actually will always hop to a single specific orbital, because if you just would work on a basis where you can hop to 2 orbitals, then you will hop to them with a specific phase and amplitude, and therefore just the linear combination will be the single orbital to which you hop. And that is the same through here. We get one ligand orbital, which is a linear combination with the phases that I drew here, and if you're perfectly cubic, the hopping amplitudes are the same, so it's a square root of 1/4 times each of these orbitals. That is now our ligand orbital. You get a similar picture for the other T to G orbitals, just rotated in space. If we look at our EG orbitals, then we start from an x square minus y square. Looks very similar, just rotated by 45 degrees. But that does make a difference, because the centers of our atoms for the oxygen atoms is not changed. And now you can hop, making sigma bonds instead of pi bonds. into these and you get linear combinations. Again, the hoping in all four directions has equal strength, so you get square root of 1/4 of each of these orbitals for your ligand orbitals. So in this case we have pi bonds, and we get the T to G orbitals. In magenta, the impurity orbitals. In green, the ligand orbital. And in this case we have sigma bonds. And we get the EG orbitals. And our ligand orbitals are just given by having your mean field Hamiltonian acting on the impurity orbital that we took into account. So within ligand field theory, we can first have a look at our basis. The one particle basis is given by the D shell and a ligand shell. When we look at d orbitals, or an F shell and a ligand shell, and the degeneracy is 2 times 2l plus 1, and the same degeneracy happens for the ligand shell, because each orbital can hop to a specific linear combinations of the orbitals outside. Now, in many electron bases, we can start from the configuration defining our formal valence, dn ligand 10, and in this case there are 10 over n states. That would be the basis you pick in a crystal field calculation. But now we include the other configurations where you can hop with 1 electron, or you can hop with 2 electrons, or you can hop with m electrons. And this stops at d10 L10 minus n. Now our many-body wave function is then a sum of m is 0 to 10 minus n, and then a prefactor that tells you how much the contribution of each configuration is, and then a sum where we have the prefactor telling you how much each states contribute to a specific configuration, and then a sum over the specific state within the configuration dn plus m ligand 10 minus m. So J goes from all possible states, which is the binomial over the 10 over the number of electrons on the d side times 10 over the number of electrons on the ligand side. Now with this we can also have a look at the occupation of electrons. So the number of electrons that we really have locally is given by the sum m is 0 to 10 minus n, and this is now the formal valence. And let's include here the difference between the real and the formal number of electrons, and n formal plus m is the number of electrons that you have in each configuration, and alpha n is then the prefactor of that configuration. Sum over j of alpha j n norm squared is equal to 1. Now we can have a look at the eigenstates that we get, and we've already seen for our crystal field case that you get locally a splitting into the atomic terms that are then perturbed and split even further by the local crystal fields. We argued the possible splitting based on symmetries, and in that respect there is not much going to change, except that we have now not only a single configuration but many different configurations. So if we look at our energy level diagram, then in just a configuration space we have the configurations dn ligand 10, dn plus 1 ligand 9, dn plus 2 ligand 8, and the energy difference here is something given by the epsilon d's, epsilon l's, as well as the Coulomb interaction. But in order to simplify our equations, we're just going to call this energy difference delta. Then I know that my energy has to be parabolic in U, so the energy difference between the next two configurations is delta plus U, and then between the next configurations is delta plus 2U, etc. Now when you include the interaction between the configurations, you will find that you have level repulsion, so these levels will go down, the next levels will go up. First of all, you have the multiplet splitting. So this is the multiplet splitting. And then we have the interaction between configurations. And that will bring down the lowest configuration and split them even further. Into many different states. Still, you can track from which configuration they come. If your hopping is small, if your hopping is big, you get large mixings between the states. That said, you still have the same number of states here that we had before, 10 over n, which is just given by the multiplicity that we have for our lowest configuration. That also means that many of the symmetry properties of our lowest set of states is just given by the symmetry properties of the dn configuration, and most for all, if there is no phase transition where one configuration becomes lower than the other configuration, this ground state symmetry properties are completely determined by the crystal field ground state symmetry properties. So that allowed us to do crystal field in the first place. It is not that you can do crystal fields because locally the potentials are the leading interaction. It is because, well, you are symmetry conserving in your states. Let's have a look at what this means by having a look at nickel oxide. And in nickel oxide, as we said before, the formal valence becomes 4s0, 3d8. So n is 8 is the formal valence. If you calculate what the real occupation is of the d shell, then this is about 8.2 electrons in the d shell because of configuration mixing. Now, because our formal valence is 8, you start with a triplet F that then by the crystal field splits to the lowest ground state triplet A, but in all cases you are in a triplet state. So our spin is 1. Well, that means that we have a degeneracy of the state with SZ is -1, 0 or 1. And let's put here a tilde above, because what is valid is our degeneracy. The degeneracy will never change when you put in additional interactions. This is an integer number of states, and that is the important thing that you cannot just change continuously. The expectation value of the S-square operator or the SZ operator is of course something that is able to change continuously. What does this mean is that if you look at the Zeeman effect, you put your atom in a magnetic field, then it will split into 3 levels. And that's an integer number. That's where your quantum in quantum mechanics comes from. They split with an energy delta E. If you now do an NMR experiment, you start in the ground state, you should be able to see 2 possible excitation levels. If you heat up your system, you get a Boltzmann population of the first, and you get 3 possible excitation levels, 2 at positive energies and 1 at negative, or 1 positive and negative energies, the Stokes and anti-Stokes lines in your system. So if you look at specific heat, then the multiplicity of your state that enters here is 3, which then determines a lot of the statistical properties of your system. Now, if you want to calculate what delta E is, we have a look at the magnetic moment. And delta E is given by the magnetic moment times your field. You can put in a mu Bohr if you want. And our magnetic moment is in nickel oxide about 1.8 mu Bohr due to the spin. If you include spin orbit coupling, it will also have some angular momentum, so that this is not something that you immediately can see in experiment. But of course, in a pure spin theory based on formal valence, you would expect 2 mu Bohr. And this 1.8 is a reduction of the spin moment due to covalent interactions. That becomes even larger for spin-and-a-half systems, just because your starting spin is smaller. And you always have some covalency. So for covalent compounds, you should expect that the local moments are reduced due to covalency. But of course, degeneracy's number of states is not something that you can change. And it is this number of states that you capture with the symmetries of the formal valence, because you just started from a small Hilbert space, then you let it interact, but then the number of states that you have here should be represented later on. Because in quantum mechanics, states do not just disappear or get generated. And that's the power that you have to start from smaller Hilbert spaces and then subsequently enlarge them or get effective parameters within that small Hilbert space. So this is ligand field theory. With the use of ligand field theory, you are able to describe many material properties. We actually now can also understand why in crystal field theory you need different parameters when you describe excitations in the very low energy regime, so magnetic excitations or excitations going up at higher energies, the optical transitions. If you look at your effective charge transfer energy delta, then the charge transfer energy becomes very small for the top level of the multiplets, because they're the top of the multiplets of the dn configuration are very close to the bottom multiplets of the dn plus 1 configuration. Actually, in nickel oxide, the top multiplet of the dn configuration, or singular S state, is above the lowest multiplet of the dn plus 1 configuration, so that you even get an inversion there of the charge transfer energy or the effective charge transfer energy. And therefore the crystal field effects for the top part of your multiplet are different from the bottom part. And that is in crystal field theory language. You can't capture this because you only have one parameter set for all of them. In ligand field theory, that follows quite natural. So within ligand field theory, you're now already able to describe the low magnetic excitations as well as optical excitations within one theory. It's still not perfectly or very accurate. It's very often accurate enough, but if you really want to have predictive power on energy scales, that are on the milli-VV range, it's definitely not there. For that you would need to expand your basis set even further. But of course locally you're on an exponential growing Hilbert space. And if you want to go away from your strongly correlated systems, nice band gap insulators where charge transfer fluctuations or charge fluctuations locally are small, then of course you need to also include your bath on a more realistic level. In the next two videos I want to show you some examples of how this works for nickel oxide and copper oxide, where you can also compare things to experiments, just to give you some idea of well, the possible excitations that you can look at and how these systems then look in real life. And then after that, in the next series of lectures, we will have a look on improving the way we represent the bath, still with the idea that any approximation you make to your bath that doesn't change the Green's functions that are of interest will not change the response functions that you can calculate from those Green's functions, and that will then not change the way we predict observables that you can make. And as long as you have a theory that predicts all observables, you're perfectly okay. Thank you very much for your attention. Stay healthy. We see each other later.